In this video, we're going to do an example where we find the Fourier cosine series for the function f of x equals x on the interval from 0 to pi. Alright, so the pi here is our value of L. So L equals pi. So because we want the Fourier cosine series for this, what we want to do is we want to approximate our function as a Fourier cosine series. So as a naught over 2, so some constant term, plus the sum from 1 to infinity of a sub n times cosine of n pi x over L. And there's one simplification that we can make here. So notice that n pi x over, so our value of L is pi. So if you plug in pi there, the pi's cancel, and we just get nx. So let's use that to simplify this, this argument here. So we have cosine, and this just becomes cosine of nx here. All right, so we want to write our function in this way. So now we need to determine what these coefficients are. So let's begin by reviewing what are our formulas. So we're going to use the fact that a naught over 2, the constant term, is the inner product of our function x with 1, and then divided by the inner product of 1 with itself. So in other words, this is sort of the coefficient of what we get when we take our function and we project it onto the span of 1, the constant function. All right, so we're going to use that, and the formula for a sub n is, so this is from projecting x onto the cosine terms. So look at the inner product of x with the cosine term, cosine of nx, and then divided by the inner product of cosine of nx with itself, with cosine of nx. All right, so we have these two formulas. So let's begin by figuring out what a naught over 2 is. So let's begin with a naught over 2. Okay, I don't want to go that far. So a naught over 2. So let's evaluate what these two inner products are. So the inner product on top is going to be the integral from 0 to L, which in this case is pi. Okay, and then I'm integrating x times 1, which is x, and then dx. So notice that my integral goes from 0 to pi instead of negative pi to pi, because we're doing a cosine series. The same thing would be true with the Fourier sine series. The other way I can sort of see that is with the Fourier cosine series or with the Fourier sine series, our function is going to be defined on some interval that goes from 0 to L. So our integrals have to do the same. They're also going to go from 0 to L. Okay, so we have that, and then on the bottom, we're going to have the integral from 0 to pi of 1 times 1, which is 1. So 1 dx. So we can do the antiderivative of x, which is x squared over 2. We evaluate that at 0 and pi, and then divided by the integral. Actually, this one we could just do. This one's just pi, because this is sort of the area under 1 from 0 to pi, and that's just pi. So plugging into the numerator, I get pi squared over 2 minus 0, so I don't need to write that, divided by pi, and then I can cancel the pi to get pi over 2. So that is our constant term. That's what a naught over 2 is. Now let's find a sub n. So a sub n is the inner product of x with cosine of nx divided by the inner product of cosine of nx with itself, cosine of nx. So on top, we have the integral from 0 to pi, x times cosine of nx, cosine of, let's write that a little bit better, cosine of nx dx. And on the denominator, we have the integral from 0 to pi of cosine times cosine, so cosine squared of nx dx. All right, so we have these two integrals. So first, what I want to do is I want to talk about a computational tool to help us see what the denominator is. So we did a really similar thing with just Fourier series. We talked about a computational tool for these cosine squared terms or these sine squared terms that we get on the denominator. So recall what that was. So when we had the integral from negative L to L of either the cosine squared term or the sine squared term that shows up in a Fourier series, both of those were equal to L. So we saw that before in section 10.3. So what I want to do now is I want to somehow use that to quickly figure out what the integral of these would be if instead I go from 0 to L. So the key idea there is that cosine squared is going to be an even function. And the same thing is also true about sine squared, because an odd function times an odd function is going to be an even function. And when we look at the graph of an even function, so I'm going to draw some axes. So if I draw a graph now, so let's draw a graph of some even function. So it's going to be symmetric about the y-axis. So let's draw symmetric about the y-axis. And if we look at the area under this from where negative L is to where positive L is, so if we look at that area, these formulas are saying, so whether this is the graph of cosine squared or whether this is the graph of sine squared, and actually this particular graph I've drawn is not going to be cosine squared or sine squared. It's not what they look like. But I'm just trying to get at the concept behind, oh, these are even. Here's what an even graph looks like. So these integrals are L. So that means this whole area should be equal to L. And because it's symmetric, that means each piece of this should have an area that's L over 2. So that means the integral of cosine squared from 0 to L is going to be L over 2. And the same thing for sine squared. It's going to be L over 2. Because that's this region over here. That's this region from 0 to L. So that's how we can quickly see what this denominator is. We use this computational tool, and we got that this was L over 2. And in this case, that's pi over 2. So to recap, with those terms of the denominator, those cosine squared terms or those sine squared terms, when we're integrating from negative L to positive L, they end up being L. When we do these Fourier series, cosine series or these Fourier sine series, and we integrate from 0 to L, it'll be half of that. It'll be L over 2 on the denominator. All right, so we still got to figure out what this integral is on the top. So at this point, pause the video for about 3 minutes and try to evaluate this integral on the top, because that's the hardest part of this, I think. 4, 3, 2, 1, pause the video. Pause the video and try to evaluate this integral on the top. All right, so hopefully you did that. Hopefully you've paused the video to try to evaluate this integral that we have on the top. So this integral that we have on the top, we have to do this by integration by parts, or IBP. All right, so let's go ahead and do that. All right, so I've copied down that integral that we're trying to figure out, and we've said that we want to do integration by parts on this. So let's set up what we want these things to be. So I need to say what u and dv are. So we're going to let u be x, because x will have a really nice derivative, and dv will be the other stuff. So I'll let it be cosine of nx dx. So remember again, when we do integration by parts, when there's sort of a polynomial term like this, like x, we usually like that to let that be u, because when we take the derivative of it and write du, that'll be a simpler polynomial. It'll have lower degree. So du, the derivative of x, is going to be 1 dx, or I can just write dx. And the antiderivative of cosine of nx is sine of nx over n. All right, so now let's plug these into our integration, into our particular integral here. So we'll get uv, which is x sine nx over n, and then evaluated at 0 and pi, minus the integral from 0 to pi of v du. So that's going to be sine of nx over n dx. All right, so let's go ahead and continue to simplify and evaluate this. So with this first fraction, when we plug pi into this, we're going to get sine of n pi, and that's 0. When we plug 0 into this, we'll get 0 times sine 0. Both of those are 0. So this first fraction is 0, so that's nice. Okay, so we have 0 for the first fraction, and then now we got to do the antiderivative of this sine nx over n. So the antiderivative of that sine is going to be a negative cosine term. That's going to make this negative in front become positive. So I'll have plus, and we end up getting cosine of nx divided by n squared. Okay, and then we have to evaluate this at 0 and pi. So plugging in, we will get cosine of n pi over n squared minus, and now plugging 0 in, we get cosine of 0 over n squared. The cosine of 0, we know what that is. We know cosine of 0 is 1. Okay, and cosine of n pi, we've seen what that is as well. That's going to be negative 1 to the n. So what we have now is this whole thing becomes negative 1 to the n minus 1 divided by n squared. So that's what the x cosine nx integral becomes. All right, so we are ready to plug that back in to our expression for a sub n. So let's remind ourselves, a sub n was this fraction here. We've now figured out what the numerator is. So the numerator is what we just determined. We just determined what that is. All right, so let's go ahead and write that. So the numerator here is going to be negative 1 to the n minus 1 over n squared. That's what we're plugging into the numerator. And then this integral on the bottom, we had worked that out already as well. That was pi over 2. This is what we got using our computational tool. Okay, so now if we simplify this, when I divide by pi over 2, that's the same thing as multiplying by the reciprocal. And if we did that, we would get, the 2 would sort of come to the numerator, and we get 2 times the negative 1 to the n minus 1. And then the pi would end up multiplying the n squared. So we'd get pi times n squared in the denominator. And that's what a sub n is going to be. A sub n is going to be this fraction. So at this point, we have figured out our coefficients. So we're ready to write down the Fourier cosine series. So x is approximately equal to, so the constant term, remember, was pi over 2. This was the constant term. We had figured that out earlier. Constant term, do we have that? Yeah, let's scroll it down a little bit. Constant term, yeah, we had gotten a naught over 2, and it was pi over 2. So that was a constant term. That was a constant term. And now we figured out what this other coefficient is. So a sub n ended up being this. And that's the coefficient of the cosine term. Okay. I noticed that we don't have any sine terms in this because we were finding the Fourier cosine series. All right. So what I want to end this video with is sort of a follow-up question for you to think about. So in this problem, we were looking at our function on the interval from 0 to pi. But I want you to think about how would this change if instead of that interval, if we did this on the interval from 0 to L. So that's sort of a question to think about afterwards. So I'm not going to talk about what this is, but I would encourage you to really think about how this would change.